Okay, let's try that. Should come on in just a second. Can you confirm for me if I have sound? Somebody? Okay. What do you notice about these bits? So when we're doing this encoding, what do you notice about these things? Yeah, I got it. Thank you so much. What do you notice about these ones up here? Are they being used? Not at all, right? And then we will actually see that the total number of, so note, I guess I won't rewrite this, but I'd like to kind of call attention to it. In the fixed point data class, it's kind of useful in the sense that we get to see how to encode fractional numbers. But the fact of the matter is, when we look at the leading string, all of this information was wasted. And what I mean to say is, this one is not particularly interesting from the standpoint of the trailing information. We're not really losing anything. But I could very, very quickly change like 1/4 to 1/5. 1/5 would be an infinite decimal representation after the radix point. And the moment that I do that, I actually lose information because I'm storing useless bits. So one of the things that we're going to do today is develop floating point. And one of the reasons that we do floating point is that in fixed point representations, fixed point means that I can't change the location of the point. It's actually fixed. And that means for a whole class of numbers, I waste bits. Bits are expensive in the sense that they are the kind of currency of data storage. And so the whole concept in fixed floating point is to allow us to use every bit possible. You all will see this in your lab for any fixed point data class, depending on what parameters of the number of leading bits and what parameters I use in the fractional bit, has a limited range. Because I fixed where the point is, there's no way to get above this value, which means that I have one data class that is basically stuck in the number of things that we would use, the number of things that can be stored in that class. So what we're going to talk about today we talk about the fundamental currency data class to do calculations on digital computers. Which is floating point numbers. Let me ask you this. When we were in signed integers and unsigned integers, what were the data classes that we used to represent that in MATLAB? So let's do unsigned, for example. UN16, UN8, UN32, UN64. Could you guess what we might study in floating point numbers? Yeah. In this class, we're going to do a training regimen. So we'll call this binary 8, binary 16, binary 32, and binary 64. The first two are going to be used for, so this is what we're going to call training. This thing is also known as a single, and this thing is known as a double. So these are non-native to the MATLAB computing environment. These things are native to the environment. Okay. I think I'm over here. Yeah. So yeah, I guess we'll take a look at our first example here to get our head around this, and we'll call this example 6.3. And I think you all said, I always forget about this. for now, I'd actually like to do this. So let's set y to be equal to 1 over 2 to the 10. So, let's see, we go over to here. Y equals 2 to the negative 10. And then let's go ahead and format long so I can actually see the entire thing. And perhaps I need to do this. Let's try again. Okay, so let's see. So this is something like 0.0009765,625. 9765625. So if I go back to here. All right, so that's that number. And then this thing right here was the representation in decimal. What is the corresponding representation in binary? So if I actually wanted to convert that to a binary number, what would that be? Yeah, so it would be 0.123456789 and a single 1 under. And the moment we're in that paradigm, one of the things that's really interesting is that in a fixed point data, I would actually have to store how many different values. So like if I'm doing this in fixed point, how many different entries would I need to store prior to the one non-zero entry? Yeah, 9 in the forward. So what's the minimum size that I could store this exactly in fixed point? Yeah, I guess you could say 0, 10, huh? Yeah, so you could have 10 bits, but if we're sticking with 16, 8, 16, 32, 64. Yeah. I mean, assuming that your trailing and your leading are the same. So one of the things that I'll say immediately is we kind of know this concept from scientific notation. What can I do right there? So at this point, right here, how could I represent this number in an equivalent way, but shifting the non-used digits? Yeah, so what we would say is like, let's go ahead and float that point over. So how many places are we floating it? 4. So we'll say to ourselves like, okay, I can actually look at this number as, so if I look at y is equal to 1 over 2 to the 10th, this is going to be 0.0009765,625. And then would you agree that I could write it like this? What is 10 to the 4th times 10 to the negative 4? That number is 1. Okay. But right now we're associating them like this. There's no reason why I have to keep that association. One of the properties we know of real numbers is I could reassociate them so that first I look at those two and then I just track on the end that this is 10 to the negative 4. What would happen once I do that? Yeah, this would be 9.765625 times 10 to the negative 4. And that's what we call scientific notation. And in this case, in decimal form. And the whole concept of scientific notation is now instead of having to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different digits, I can actually store that exact same number in decimal as 1, 2, 3, 4, 5, 6, 7 plus an exponent, right? Which means that for the same cost in digits, for a smaller cost in digits, I get the same number stored. It's just that I have to actually track that thing. So, one of the things that we're going to talk about in decimal. So if I look at this thing, we said that this was 0.001231231. All right, now how would I write that in scientific notation in binary? Well, we know that this is, yeah, 2 to the, oh, sorry. Say it again. I can shift that decimal point over 10 units. The moment that I do that, I need to track that indeed, to get that new number, I've shifted it over 10. So to go back to the old number, I need to shift it -10. So this is 1.0 times 2 to the 10, which means that a number that was stored in 10 bits is now stored in a single bit as long as I can track the exponent. As long as I have access to what that exponent should be, I'm fine. Oh, sorry, yeah, sorry, of course. Because this is the one up front, right? Okay, so this is the source of inspiration for floating points. What do we mean by that? What do you notice in each of these examples? What's happened to the actual decimal point? It's literally floating down the string of bits, right? All right, so let's take a look at another one. And we'll do something a little different than the one that's done for you. So we'll call this example 6.4.2. And let's let y be equal to 2 to the -5th plus 2 to the -8 plus 2 to the -10 plus 2 to the -11. Okay, so let's write this out as a pure binary fraction. So this would be 0.1234567891011, right? So if I were to write that as a binary fraction, it would look like this. What would the corresponding float look like? Yeah, we would float the thing down the bit string. How many units? Yeah, 10 to the 5, which means immediately when we captured that in scientific notation, it would look something like 1.001011 times, and of course these are not tens, what they should be instead? 2. So the first one shifts the bit, the radix point to the right, and then the second one would just shift it back, which means now in scientific notation, we get something that looks like that. And I want to start calling some names out. So we're going to call this right here the leading point. If this is equal to 1, we call that normalized. So if the number in the very, very front of our floating point number was 1, we'll call that normalized. Could you guess if we call this the leading point part, what we're going to call this thing right here? Yeah, it starts with an F, actually. Yep. This is going to be called the fractional part of our number. This thing right here, always, always, always in binary representation, this is going to be the base or the radix. And in this case, when we're doing binary, that will always be 2. What do we call this thing up here? Yep, exponent on that. Yeah, so we will get there for sure. Okay, so what this means mathematically, so when we write this thing, we're going to think about the following representation. We're going to have what we call a sign. So what's the sign in this case? Yep. And this is where we go back to sign magnitude. So for every number that we do in floating point, we're going to have a sign. We're going to have what we call a leading value. And then we'll have what we call a fractional part. So let's go ahead and do this. This thing up front, what do we call that? Yep. Could you guess if we were going to store that, what we would say? What stores as positive, which stores as negative? 0 positive, 1 negative. We're going to do something really special here, which is for normalized numbers. What does it mean to be a normalized floating point number? Yeah, it means that the number is always going to be 1 in front of the radix. This is implied, not stored. So the leading part, we're not actually going to store what that leading part is, and we'll talk more about normalized and how that whole thing works. Could you guess what we call that? Well, what did we call it up there? Yep. Fractional part. In notation done in scientific computation, we call this the significand. Some people call it the mantissa, but that's kind of old school language. So significand is the string of bits after the implied leading part that store that number. And then this thing is going to be the so the calculated exponent value. And we'll talk more about what we mean by calculated exponent value. All right, so what that immediately means is when I'm looking at a floating point number, I can actually store that floating point number always, always, always in something that looks like this. So this implies that y is going to be a positive or negative 1 plus some fractional part, the entire thing times 2 to the e, where the fractional part corresponds to the interpretation of the binary string stored in the significand. Okay, so if I'm looking at quarter precision number, in binary 8, how many bits do we have? How many total bits are we using in this data class? 8. Okay, so now we look at this as binary 8 of some number y. And then what we're going to do is actually those 8 bits, I'm going to try, I don't think we've done this as much this quarter as I did last quarter, but I'm going to use capital letters to talk about raw bit strings. So these are non-interpreted. These are literally the values stored in terms of 1 and 0s, not the corresponding interpreted value of these things. And then this would be B3, B2, B1, B0. And then what I want to do is I want to talk about something, I don't know how to do this well. So we'll talk about this as bit number. Okay, this least significant bit in this data class, what's the bit number on that thing? Yeah, we'll call it 0 for now. How about this one? 2, 3. This would be 4, 5, 6, and 7. In the signed magnitude representation, what did we say about the most significant bit? Yeah, say it again. Yep. So this thing right here is going to be what we call the sign bit. And maybe I should use colors here. Maybe blue is nice for the sign bit, right? Okay. The second set of 3 bits in this case, we're going to call this a biased exponent field. So these 3 bits right here, and maybe we'll use green for this. It's not the calculated value of the exponent. It's actually an encoded value of the exponent, which is what is known as biased exponent. So we'll talk about that in just a second. Okay, could you guess what this one is? So every floating point number has what we call a sign, a leading part, which is implicit, a significand, and an exponent. So far we've stored what we call the sign and the exponent. Could you guess what the last bit is? Yeah, so these last things here are going to be called the significand. So these last four store the significand with some fractional type 1 rational number. Okay? Yeah. One of the things that's really interesting about the biased exponent, we're going to call this XS3 bias. So the way that this works is when we think about these strings, so if I thought about E and I looked at the uint, I mean, I guess it would be uint3 to be honest with you, of B6, B5, B4. In order to get the actual exponent value from the corresponding bit string, I'm going to subtract 3, right? So another way to say that is when I store the exponent in memory, I'm going to add 3 to the calculated value in order to calculate the actual bits in memory. Because, think about this, if I have 3 bits for the exponent, what's the highest number that I could possibly store? 1 plus 2 plus 4 would be 7, but then the 0 value would be 0. So the only numbers that I could store are those bigger than 0. But if I subtract 3, the top goes from 7 down to 4, and the bottom goes from 0 down to -3. So the bit string 0, 0, 0 actually encodes the value 2 to the -3. So let me show you what I mean by that. So we'll do an example. And in this one, I actually spent tens of hours when I wrote this class to begin with, putting together these examples. So I might use them because these examples actually take a few minutes to think about. So, thank you. So in this case, we'll say, let's take a look at the number 15. All right, so can you write 15 in decimal? Actually, in binary? Yeah, so 15 would be 1, 1, 1, 1. All right, let's go ahead and shift that into a floating point number. So what would I do if I wanted to shift that into a floating point number? 1, 2, 3. The first thing I would do is I'd shift the binary point 3 units to the right. But what it would mean is that I have to track that I've done that. Sorry, 3 units to the left. So this would be now 1.111 times 2 to the 3. And here I have a positive. Okay. So let's go ahead and think about this. This thing right there is called what? That's called the sign. Is the sign bit positive or negative? Positive. We're going to call this the implicit leading part. So we are not going to store that. This thing right here, what do we call it? What do we call it in our... Yep, this is the significand. And then this thing right here is going to be the calculated exponent, 3. So let's go ahead and write that out. So in this case, we have that the exponent value is 3 base 10. How would you write 3 base 2? Yeah, so this would be 0, 1, 1. But the claim is we're going to think about this as the actual raw bit string. So the interpreted value of the bit string, B6, B5, B4, minus some bias. So this is going to be the bias that we talk about. And we'll talk more about what this means as we go on. Right now I'm just giving it to you. As I teach this class more and more, I'll be able to actually justify where that comes from. What did we say about the value of the bias from the standpoint of binary 8? Yeah, we're gonna, whatever that value is, we're gonna subtract 3 from it. So in particular, whatever this bit string is, the bit string that we're looking for is B6, B5, B4. When we subtract the number 3, we want to get the number 3. Okay? Well, this is the thing that I'm looking for. How do I get that thing if this is on the other side? What can I do in algebra? This is the unknown. What am I going to do here? Bring it to the other side. So this is B4, B5, B6 is basically 3 plus 3. What is 3 plus 3? 6, which is E plus K. This is my unsigned bit string, which we'll talk about in a bit. Okay, so what is the unsigned bit string that stores this value? How do I store 6 as a binary number? 1, 1, 0. All right. So what value of the signed bit do we have? What's the signed bit here? 1 or 0? 0. So the signed bit is 0. What's the value of the fractional part? So if I think about this in binary 8, 0 for the signed bit. What's the exponent field? What did we claim about the exponent field? 1, 1, 0. How about the fractional part? 1, 1, 1, 0. This now is a binary representation, but in particular, this is what we call binary 8. So if I go back into MATLAB, and I go on to Cleve's laboratory, and I forget the number we used right now, 15, right? Okay, so for those of you that showed up a little late, earlier today, I showed how to download Cleve's laboratory. Cleve Moeller is the guy that wrote MATLAB. And here it is. So let's go ahead and click in 15. Okay, we're going to go into binary 8, and then here's the claim. What I want to know is, in binary 8, what's the bit string? Well, read it off to me. 0, 1, 1, 0. So that means that the stored value of the exponent is 6. 6 minus 3 is 3. So the calculated value of the exponent is 3. And then I have an implicit leading bit. So there's actually a 1 point what? 1, 1, 1, 0. In hex, I'm not sure how 3 hexamet. This doesn't make sense to me. Say it again. You would imagine, right? But I think there's because if you look at this, if it's two 4-bit sequences, then there should be no 0 in the front, right?
Right.
Yeah. So we'll come back to that in a bit. I'm not sure if he has a mistake there or if what he's doing is he's using the sign bit to be separate. We'll take a look at that as we continue in this. Okay. So what I'm going to do is I'm going to propose the following. So let's look at what we call. Do you want to go forward or do you want to go backwards?
Yeah, so it's assigned to it, but maybe
Yeah. So let's do another one of these. What if we were to do y equal 4 plus 1/2? All right, so what I want you to do is on your own right now, I want you to see if you can convert this into the appropriate floating point number and then check your work in MATLAB. Maybe I should keep this up, right? Like that? Is that enough? Can you see enough? So off page, I'll actually do this with you. So you're converting this number into its corresponding binary 8 representation by hand, and then checking your work in MATLAB. You want more help with that? No? Michelle says she's in.
We're doing 8 bits?
Say it again.
We're doing 8 bits?
I didn't.
Like what we just discussed, we're doing 8 bits?
8 bits, binary 8, yep.
Okay.
I should have done negative, huh? Yeah. What did we say it was? 4.5, right? Got it? I'm going to say some words right now. We're going to come back in a sec. We'll take a break. But I had some really good, what I would call like valuable feedback from students. Many students, I believe, are thinking, I thought this class was going to be a coding class, and we're talking about data structures. I think that's a really, really good feedback. I genuinely believe if you plan to do scientific computation and numerical analysis, that understanding how numbers are stored in a computer and what type of errors that results in sets a foundation for understanding numerical analysis at a grand scale. When I was designing this class, this is only the second quarter that I've done it, I made a decision, which is I want to give you all deep understanding of the numeric data structures in MATLAB. I have not seen this other than so one of the other really challenging parts of this class is that, raise your hand if you've had to take computer architecture or you are taking it right now. Okay, so some of this is review for you all, right? You haven't seen it in MATLAB, but one of the things that's really tough about this class is just because you've seen it doesn't mean that I can assume that all other students have seen it either, right? And so when I'm structuring the coursework, I'm structuring it with the assumption that I've had last quarter, and I think at least one this quarter, that has never written a line of code. I think this is really exciting. I don't know that you all yet have the perspective that you can appreciate that. So a lot of folks think like, oh, what's exciting is when I write code to do really cool stuff. And eventually, yeah, I will get to a place in our class where we can do really cool stuff. But the fact of the matter is, I think this is really cool. What this ends up meaning is that anytime you encode numerical data in MATLAB, which I would claim is anytime you do any calculation in MATLAB, you have a complete representation of what's going on internally for yourself, and that you have the entire structure to be able to speak really intelligently about that. We will next week, hopefully we'll finish this by the end of this week, and then next week we'll get back into syntax. We'll talk about loading stuff. We'll do some kind of fun explanation or explorations with what I'm thinking to be matrices. But I do want to address that. The reason that I'm doing this is I want you to have that foundation. It's tough having this be my only quarter, the second quarter that I'm teaching the class, because the number of hours that I've had to develop it is not equal to the number of things that I want to develop. But I'm really excited that starting at the end of break, you all will be able to convert numbers from decimal into binary 8 or binary 16, eventually binary 32 and binary 64, because what that means is anytime you look at numerical calculations in MATLAB, you're not stumped by what's happening underneath, right? The one downside is you will have to actually make a decision to go on and use MATLAB in your career, and for the things that we didn't cover in syntax, fill those in. But when I think about the challenge of figuring this stuff out, so what's going on in the guts of MATLAB versus figuring out how to code, how to figure out how to plot stuff, one of those is very hard, in my opinion, to do alone. One of them is not so hard. So that's where I'm coming at. Let me shut up. It's now 10:53. Can we start again at 11:03? And then we'll go on to the next